In this video, we're going to start looking at how a balanced chemical reaction can help us understand the relationships between different reactants and products. And this whole idea is known as stoichiometry, which is just the relationship between the relative quantities or relative amounts of substances taking part in a reaction or being produced by a reaction. So what this concept of stoichiometry allows us to do is to understand if I react a certain amount of material, I can predict how much product is going to be produced. Or if I need to produce a certain amount of product, I can figure out how much reactant do I have to start with in order to get my target amount of product, or any other relationship between different substances in a reaction. If I produce a certain amount of one product, how much of the other product will I get? Whatever you need to figure out. So the way we do this is using the coefficients in a balanced reaction. And this is why having a balanced chemical reaction is super, super important, because the coefficients in a balanced reaction are just ratios of how much stuff in terms of moles is either being consumed or produced in our reaction. So the coefficients in our balanced reaction represent mole ratios, or the relative amounts of reactants consumed and products produced. In our chemical reaction. So for example, if we look at the reaction that produces water from hydrogen and oxygen gas, what this represents is hydrogen gas and oxygen gas forming water, but more specifically, it represents 2 moles of H2 reacting with 1 mole of O2 to produce 2 moles of water. So what this reaction is telling us is that for every 2 moles of hydrogen that react, 1 mole of oxygen must react. So for every 2 moles of hydrogen that react, 2 moles of water will be produced. And we can use these as ratios to kind of scale that up or scale that down accordingly and interconvert between moles of different reactants and products. So that ratio of amounts is always going to be preserved, regardless of how much stuff is actually reacting. So, for example, if I react, considering the same reaction here, just copy it down. So it doesn't get lost when I scroll. Using the same reaction, if 2 moles of H2 react, that's exactly what it says in the coefficient. So that's really, really straightforward. We can predict how much product is going to be produced. If, let's say, 3 moles of H2 react. If for every 2 moles of H2 we get 2 moles of H2O, we're always getting the same amount here. So that ratio is going to be preserved. So if 3 moles react, 3 moles of H2O. are going to be produced. So in that case, we have equal amounts since our coefficients are the same on both sides. However much H2 we start with, we're going to get the same number of moles of H2O produced. You'll notice for O2, it's a little bit different. When 1 mole of O2 reacts, we get 2 moles of water. So however much oxygen we start with, we always get twice as many water molecules produced, or twice as many moles of water produced. So if I started, let's say, with 6 moles, I'm going to get twice as many moles, which would be 12 moles of water produced. So here, the coefficients are pretty simple. I went with simple numbers of moles. It's pretty easy to see this relationship that we're, equal numbers of moles of hydrogen and water, but we get twice as many moles of water as oxygen. So what we're actually doing here, if we wanted to show our work, show how we figured this out, which is something you will need to be able to do, and when the numbers are not as straightforward, you really need to do, is what we're really doing here is using our coefficient ratio as a conversion factor. So this is just like any other unit conversion, and I cannot stress that enough, that we are canceling out units of moles of one thing and we are converting into moles of a different thing. It feels a little weird because it's still moles to moles, but it's moles of different substances, so it is still a unit conversion. So for example, still going back to that same reaction, let's figure out how many moles of O2 must react in order to produce 0.546 moles of H2O. So we've identified a particular amount of product that we want to produce in this case, and we're looking to figure out how much reactant do we need in order to produce that amount of product. Specifically, how much oxygen do we need to produce that amount of product? So what we want to do here is use our coefficients. We are converting from moles of water to moles of oxygen. Note that invisible coefficient is really a 1, so keep that in mind. We know that we have 0.546 moles of water that we are looking to produce, and our end goal is to find how many moles of O2 we need to react in order to do that. So just like any other unit conversion, the unit that I started in, I need to cancel out. So that means in my conversion factor, moles of H2O needs to go on the bottom so that this and this will cancel out. The new unit I'm trying to get into has to go on the top so that we will be left with moles of O2 as our final unit. So now what goes in here as your conversion factor is just these coefficients. The reaction is telling you that some number of moles of oxygen predictably reacts to produce a particular amount of moles of water. So all we need to do here is plug in our coefficients from our balanced reaction. To find that we would need 0.237 moles of O2 to react in order to produce our target amount of water. Now, when we're working in the lab, as we've talked about before, we can't really directly measure moles. So what we're usually doing is really thinking in terms of mass, and we already know how to convert between mass and moles, and that is by using the molar mass of a substance. So we can combine our understanding of molar mass with this new understanding of coefficients in our reaction really as a conversion factor or as a mole ratio to be able to convert between grams of one substance and grams of a different substance. We just need to take all of the right steps along the way. So if you're starting with grams of one thing, the first thing you always want to do is convert into moles. Stoichiometry, our coefficient ratio, represents a mole ratio. So we have to work in moles for that coefficient portion. So if you're starting with a mass, you want to convert to moles first of that substance, and we use the molar mass to do that. Remember that the molar mass tells us that 1 mole of that substance is equal to some number of grams of that substance. So that's our conversion factor between grams and moles. We can then use our coefficient ratio, like we just saw, to convert from moles of one substance to moles of another. And then if we want to end up with a mass of this other substance, we just need to use the molar mass of that substance in order to do one more conversion from moles to grams. So the only new piece here is really this middle step of coefficient ratios. You already know how to convert from grams to moles and from moles to grams. We're just adding on this piece of converting moles of one thing to moles of a different thing using our coefficient ratio. So why don't we give that a try? So let's say if 1.5 grams of H2 gas reacts completely, what mass of water will be produced? Sure. So why don't you pause here, give that a try on your own. Again, the only new piece is this coefficient ratio that we looked at how we use that in the previous problem. Everything else is just molar mass conversions, which we've done before. So take a minute, look at that on your own, and then we'll go through it together. So we're still dealing with the same reaction here. And what we need to think about is sort of on this flowchart thingy, where am I starting, where am I ending? And that kind of tells you what steps you need to take along the way. So we are starting out, the thing that we know to begin with is a mass of H2. So for the purposes of this problem, let's call A H2 for right now. We're starting with grams of hydrogen. So we're starting out over here. Begin. And what we want to know is what mass of water. So we're looking to end up in grams of water. So for this problem, let's call B in our little flowchart water. So that means that we want to end up over here. So we have to take all the steps in between, and we have to do them in the proper order. We need to take grams of H2 and convert it to moles. We then need to take moles of H2 and convert it to moles of H2O. And finally, we need to convert moles of H2O into grams of H2O. And if we recognize those steps, we can figure out all of the different pieces of information, all of the different conversion factors that we need along the way. So first step is going to be grams to moles of H2. We know that 1.5 grams of H2 is reacting. Again, thinking in terms of like any other unit conversion, I need to cancel out the unit I started in, so that one goes on the bottom, and the new unit I want to end up in goes on the top. My conversion factor from grams to moles is my molar mass, which always tells me that 1 mole of a substance is equal to some number of grams of that stuff. For H2, it is 2.016 grams per mole. So in this case, we're dividing by the molar mass because we need those grams to cancel out. And we get 0.7440 moles of H2. So we started out with a mass of H2. We used our molar mass of H2 to convert that into moles of H2. Now we can take moles of H2, or 40, and the next thing we want to do is convert it into moles of the other substance we're interested in, which is water. So again, original unit needs to go on the bottom so that that cancels out. New unit goes on the top. So our conversion factor here is our coefficient ratio from our balanced reaction. So our coefficient ratio tells us that 2 moles of water is produced by 2 moles of hydrogen. So we end up getting the same number, in this case, of moles of water produced. Colors haven't I used? Red, sure. And then last but not least, we need to use the molar mass of water, or other substance, to convert from moles of water to grams of water. So again, original unit was moles of water. That needs to go on the bottom so that that cancels out. New unit that we want to end up in is grams of water, so that goes on the top. Our molar mass tells us that 1 mole of water is equivalent to 18.015 grams. And that gets us to our final answer of 13.4 grams of water is produced when 1.5 grams of hydrogen reacts completely. So we can see that we're kind of following the steps in order here, going through each of these conversions using the appropriate conversion factor. We could also write this out all in one step, and that would be totally fine, and we can see how everything cancels there as well. So we could do the exact same process in one line, that we're starting with 1.5 grams. We know that we need to convert grams to moles, so we divide by the molar mass, and then we need to convert moles of H2 into moles of H2O. So we use the mole ratio of 2 to 2, and then we need to convert moles of H2O to grams of H2O using the molar mass. So this is exactly the same process, starting with my mass of my reactant in this case, which was where we started. Then we needed to use our molar mass of that substance to convert from grams to moles. We can see that grams of H2 cancels grams of H2 here, just like it did up here. Next step in our process was to convert from moles of substance A to moles of substance B using our coefficient ratio, which was the next thing we've got right here. We can see that moles of H2 cancels moles of H2, just like it did up here. And then last but not least, we needed to take that resulting number of moles, use the molar mass of our second substance, water in this case, to convert to grams. And we can see the way that we have things set up. This one's purple. Keep the color code the same. That moles of H2O cancels moles of H2O, and the only thing left not canceled out here is grams of water. So this is just the same process, but done as a single calculation instead of 3 separate steps. Either way is fine with me. Whatever makes the most sense to your brain. So these can be a little bit confusing at first. I strongly recommend that you are including units when you're showing your work, and that you get in the habit of actually showing your work out for these, because it's really, really easy to get this, in particular, this ratio upside down is the most common mistake that I see for people. In this case, it doesn't matter because they're the same. But like back in the previous example we did where it was 1 to 2, people get really confused about like, well, does the 2 go on the top or the bottom? Do I multiply or do I divide? And if you're looking at your units, it becomes obvious that you're starting with moles of H2O. So moles of H2O needs to go on the bottom in order for that unit to cancel out. And the 2 is attached to the H2O in your reaction. So wherever moles of H2O is in terms of the units in your unit conversion, that's where the 2 goes. The coefficient stays with its thing that it is the coefficient for. So strongly recommend that you are writing out your units to help you get in the habit of feeling confident knowing when you need to multiply or divide, or what goes on the top, what goes on the bottom. It's all just dimensional analysis. It's all just unit conversions with slightly unfamiliar units. So follow the flow chart in order, pay attention to your units, and you will be in great shape.